So it's 4 o'clock, so since formal methods 1 is not enough, we're here for formal methods 2. So please take away, Amanda Stjerna.
Yes, thank you. We've had one formal methods, yes, but what about second formal methods? I'm going to present my joint work with Philipp Rümmer on accelerating counting constraints on string solvers. And I promise I will make that sentence make sense to you once we're finished. So because string constraints these days are everywhere, they're usually in input validation. You might want something like find me a string that passes this validation regex, but you also want it to contain a naughty script tag. And then worst of all things, you might also have length constraints. And once you start having length constraints, that's when the bad things start. So I assume that we're starting with a bunch of string constraints that we're handing off to a string constraint solver for solving. This is an SMT solver. And we imagine that we have a bunch of these kinds of regular language memberships. You will realize at the end of this example that it's calibrated to be a great example, which is why the automata don't make sense. But we also have a substring constraint that says that string number 1, in addition to matching some regular language, has to be a substring of string number 2, starting at index I and having length n. And that's what I've been trying to visualize in this block diagram there. We also have a bunch of constraints on those indices that require that we have something before and after the substring. So this is essentially to make the case a bit interesting. The first 2 constraints can be easily handled by a regular language constraint. So that's not super complicated. It's just automata theory. Standard undergraduate automata theory is enough for that. The substring constraint is a bit more tricky. So if we assume that we have an automata-based string solver, we can take this automaton and then we can turn it into a substring accepting automaton by adding an extra transition at the beginning and the end that will accumulate the prefix and the postfix, and they will just do this for any transition. Now the problem becomes, how do we handle the counting? Usually we do this by turning this common normal automata into a Parikh automata and having it increment some register. So in this case, we increment the prefix register I when we take the first transition. And we do the same thing for n. So now we know how long the prefix string was. We know how long the content string that we're matching is. And I'm also adding a length constraint that will come in handy later. So I also count the length of the entire thing that's accepted. And that handles the substring constraint. If we use standard methods and blast this into some form of linear equations, we also get the inequalities handled for free by our SMT solver, and now we just need to count the length of the other string. We do that in the exact same way, so we just add one register that counts the length. Now we've translated this problem that is about a bunch of annoying and complicated functions into finding the intersection of these 2 automata, both that have some registers, translating them into a set of constraints and then solving them. So the problem that we handle more generally is that we have some number of products of automata. We count something using some kind of homomorphism that does some counting. I'm being hand-wavy here, which is why I'm waving my hands. And then we have a bunch of integer constraints on the final values of those counters. So this is pretty much an intersection problem for Parikh automata if you like complicated language. So this will look like this. You have a product that you want to compute, and the previous state-of-the-art method is to take this, run it through a bunch of encodings, get a bunch of these nice formulas on the right. But the problem is that in order to do this, you first need to compute the product of the automata and then do the translation. When you do that, you have exponential blow-up. That's bad. This is a real automata, but it's not this one. A second problem that you also get is that some of these constraints have a complicated Boolean substructure that comes from the fact that you need to enforce connectivity in the presence of loops. So if this transition is used at any point, you need to make sure that we're coming in through one of these, and that generates a lot of OR clauses, and those are usually expensive to handle. So the key ideas that we present in this work is a method for pruning automata terms using the underlying solver before we compute the product, so that the product is smaller. We also delay the enforcement of the expensive connectivity constraint using standard online methods, more or less. This allows us to make sure that the product is as small as possible, and we also have a splitting strategy to allow us to whittle down the automata even more before we compute them. We put this in a box that we call Catra. That's the thing we produced. Catra consists of the method itself that we call PC star. This is the thing that you can generalize and use in other products. It talks to an SMT solver, in our case the Princess SMT solver, and it Princess handles linear constraints for us. And that is the artifact that we submitted as well. So this is sort of the output more concretely. This is meant to be used by an SMT string solver. So the string solver asks this entire thing to handle a bunch of constraints that happens during string solving, and then it gets back answers of whether they're satisfiable or not. But you can also hook it in various places. So we return to the example, and I will be working through this example to show you how it works in practice. So I start by adding that both automata has to accept a string of the same length. That's why I added the length counting constraint to the bottom automata before. That will allow us to do some more pruning. This is implied, but I do it anyway. Then we need a way to go from transitions to the register constraints that we already have. So we know things about the register values, but we don't know anything about the transitions of the automata, and those are the ones we want to prune. We do that by giving each transition its own fresh variable that doesn't occur anywhere else. And they also are only given one constraint, and that's that they have to be more than 0, or 0 or more. And they represent how many times that transition is used in a solution. We can then tie those to the register values by just adding a constraint that the number of times, or the value of each register is the sum of its transitions. So for example, this variable here is exactly identical to I, because the register I appears in exactly one transition, and it's that one. The same thing happens for the lengths, and the same thing happens for n. So these transitions sum up to become the final value of the n register. So now we have, whenever we have a constraint talking about one of the registers, or the final values of the registers, we can now translate that to say something about the transitions. We also have a bunch of constraints that come from the fact that this is an automata. For example, if we go into a state, we need to come out of that state the same number of times. So that means that the sum of the incoming variables is equal to the sum of the outgoing variables, except for the initial state, which has an initial flow of 1, because we stop the automata once. So this allows us to do some reduction in variables, because whenever we have something like this, where we come in exactly as many times as we go out, we can already remove some variables from this, and using just standard equality propagation. Now it's time to start pruning the automata, and we can do that by performing linear equation solving on the equations we already have, so that in this case you can see that the values have now distributed across these sums, so that we have this. And this allows us to conclude that n has to be 2, because 2 minus n has to be greater than 0. Which gives us both an upper and a lower bound on n, and there's only one integer that fits in there, so we know that. This gives us an automata where this transition is used 0 times. That means we can remove it entirely. And these two become 1. By similar reasoning on the bounds of I also becomes 1. So now we have an automata where we know exactly how many times we take these transitions. And we also know, crucially, that we don't take one of the transitions. So now we have just a stick down there. That's a much nicer product. But we still have some more decisions that we can make. And this is mainly to illustrate. Under normal circumstances, I would compute this product straight up, because it's very small. But we can still get it even smaller if we want to. And you can see here that we have 2 choices in the upper automata of where to go. Either we go through this strong connected component at the top, or we go in through the one at the bottom. We can pick exactly one. So now we can generate a k-split for the underlying SMT solver, where we say that, okay, we pick this transition, it seems interesting, we try to isolate that one and split that into two cases. One where we don't use that transition, and one where we must use that transition. And then we hand that off. And now we get a smaller automata. So we start with the equals 0 case. And when we've done that, we can start thinking about the connectivity constraints. So now we have a much smaller automaton. We know that we're not taking the upper path. That one is no longer reachable. But we also know that this loop has something that could potentially not be 0. But that can't be, because there's no way to that state. So we add a blocking clause that says if B6 there is 0, the incoming transition, then that implies that the loop can't be used. And this will further reduce the possible things. So now it's time to compute the product. We just have these two sticks, and we can just smash them together, but you will realize very quickly that there are no overlapping outgoing transitions from the initial state. So modulo dead states, this product is empty. So we've now completely removed this case, and we would have to try the case in the k-split, and that one would have the same result, because this example is unsatisfiable, but it's not trivially unsatisfiable. So the outcome of this are these results. What you see here is simply us. So we took a bunch of inputs of this type of problem, that comes from Ostrich doing trying to solve the PyX benchmark suite, which is a standard string constraint benchmark suite. And we have implemented a bunch of different backends that solve the same problems. So to the left, you can see how many solutions we managed to compute within a 30-second time budget. And to the right, you can see how long it actually took the various backends. And the alternative we have is us, which is PC star. In the middle, we have the previous standard approach, where we essentially just translate compute the product, translate them into using standard methods, and hand them off to the same underlying solver. And to the right, we have the nuXmv model checker. And as you can see, we do slightly better than nuXmv and a lot better than the previous baseline approach on, in particular, unsatisfiable instances. That shouldn't be super surprising to you, given that unsatisfiability is easier to detect in this case. If you have a satisfiable instance, you have to compute the entire product, and that's always a bit more expensive. But from the box plot to the right, you can also see that we generally come back with solutions faster, and that's very important because we are at a leaf in a rather complicated stack of various things calling each other. So in summary, I have presented a method for computing some prediction on Parikh images of languages, or their intersection. I have shown how we can lazily materialize the products, and I have shown how we can lazily enforce their connectivity constraints instead of upfront having to encode them. And I've also showed very briefly how we can do case splitting to drive those. Thank you.
All right. Thank you. So we got some time for questions. All right, let me warm up the audience. So I think so. It seems like your technique does depend on picking the right edge to cut in order to get those smaller products. Can you comment a little bit about how well that works, how predictable that is, that sort of thing?
Yeah. So of course we tried different strategies. And essentially, so all of these rely on finding strongly connected components and then computing min cuts across them. And generally what you want to do is you want to cut as early as possible in the automata, because that makes sure that you cut away as many transitions as possible. It also helps to try to cut big components when you're trying to isolate them from the initial state. So in general, that's the strategy I went with. I tried a bunch of other things, but that's the one that works the best.
Okay.
Could any of the techniques that you have invented be backported into the things that you're comparing with? Your baseline and your...
For nuXmv, I don't know, because I have no idea how nuXmv works. I assume that it does things that are similar, because it has also has pretty good performance, and it can't possibly be computing products up front. That would just explode. So it has to do something similar, but I'm not well versed in model checking, so I don't know how that usually works. The other method is about as good as you can make it. Going into the exact details of how we implemented the baseline approach is far outside the scope of this, because it would take too long, but it essentially can't be improved further. So no, not that I know of.
So I have a very simple question. You mentioned Ostrich as an SMT solver that you use, right? So did you try other SMT solvers in combination with your approach?
So the problem is that what we need is, so the usual question that comes up is, why aren't you doing this with Z3, for example? And Z3 is word equation based, which means that you can't easily do the translation. It has completely different problems, simply. There aren't that many automata-based string solvers. I think Chow is the other one we have. The easy answer is that the integration is not super straightforward. And usually they make other trade-offs. So Chow, for example, only accepts strings that would lead to automata that don't have the problem of loops, for example.
So it wouldn't scale simply, or you couldn't?
It could be implemented, but this is pretty much the string solver that does this. It's also the one that's best in its track on SMT-COMP, which is why it's interesting to try to improve it. That's a separate result that's also in the paper. So we actually take that, the fragment that it does really well, and we make it slightly better at that one.
Okay, thank you.
I should have run out of time.
Thanks. Right. I can speak really slowly if you like. No.
Do a James Noble and start asking the question in French.
Yeah. Sure. No. So like, which one of the discrete techniques that you invented in order to get to this result, like, is the most influential? Like, which is the most powerful one, and which is the most surprising to you?
The most powerful one is the delayed product computation, because it's essentially what happens in the baseline approach is that it spends all its time doing product computation. And in fact, most of the products don't even fit in RAM, regardless of how much RAM you give them. So that's by far the most impactful one. And that's also why we started introducing case splitting, because it turns out that just doing the pruning before you compute the product will not give you enough bang. You need to further whittle down the automata so that they're small enough that you can compute the products. So I think that's the one that really gives some bang. The splitting strategy isn't hugely important. It does some marginal improvements, but really just doing it at all is what matters. There's also some trickery behind choosing which products to compute. Okay, I'm being waved off stage.
So Fernanda again.